Every time you do Gaussian elimination, you throw away half the work. You carefully compute multipliers, use them to zero out entries, and then forget them. Those discarded multipliers are exactly what you need to reverse the entire process. Keeping them gives you the single most important factorization in linear algebra, equals L times U. Any matrix A factors into a lower triangular matrix L times the upper triangular matrix U. L has ones on the diagonal and the entries below it, while U has entries on and above the diagonal. Let's see where this comes from. Start with the smallest case, 2 by 2. Take A, first row, 2, 1, second row, 8, 7. The pivot, the diagonal entry used for elimination, is 2. To eliminate the A below it, we compute the multiplier. 8 divided by 2 equals 4. The multiplier is always the entry we want to eliminate, divided by the pivot. Now subtract 4 times row 1 from row 2. For the first entry of the new row 2, 8 minus 4 times 2 equals 0. For the second entry, 7 minus 4 times 1 equals 3. The result is U. First row 2, 1. Second row 0, 3. This is upper triangular. All entries below the diagonal are 0. Now let's frame this as matrix multiplication. Multiplying A on the left by E21, the elimination matrix with 1, 0 on top and -4, 1 on the bottom performs exactly that row operation. E2 1 times A equals U. Right? We've been writing elimination this way, but nobody actually wants E times A. What we really want is A equals something times U. Now let's rearrange to get the LU factorization. We start with E21 times A equals U. Move E21 to the other side by multiplying both sides by its inverse. This gives us A equals E21 inverse times U. To invert E21, we simply flip the sign of the off-diagonal entry. E21 had -4 in the lower left. Its inverse has +4 instead. Bam, this makes sense because undoing subtraction is addition. This inverse matrix is what we call L. L equals the matrix with first row 1, 0, and second row 4, 1. Notice that L is a lower triangular matrix, meaning all entries above the diagonal are 0, and it has ones on the diagonal. Now let's verify by multiplying L times U. First row of L is 1, 0. 1 times 2 plus 0 times 0 equals 2. 1 times 1 plus 0 times 3 equals 1. Right? Second row of L is 4, 1. Right? 4 times 2 plus 1 times 0 equals 8. 4 times 1 plus 1 times 3 equals 7. And the result is 2, 1, 8, 7. That's exactly A. So we have confirmed that A equals L times U. L is lower triangular with ones on the diagonal and the multipliers below. U is upper triangular with the pivots on the diagonal. This is the LU decomposition. Here's the recipe. To build L, take the multipliers from elimination and then place them below the diagonal. Put ones on the diagonal. That's it. In our example, the single multiplier was 4, computed as 8 over 2. That 4 sits in position row 2, column 1 of L, exactly where the elimination happened. No extra matrix algebra needed. L comes for free from the work you already did. Now, to see how this generalizes, consider a 3 by 3 L matrix. It still has ones on the diagonal, and the multiplier slots sit below. Position row 2, column 1, position row 3, column 1, and position row 3, column 2. Each of those slots gets filled by the corresponding multiplier from the elimination steps. This approach was clean for 2 by 2, 1 multiplier, 1 step. But larger matrices have elimination steps that interact. In a 3 by 3 elimination, you need up to 3 elimination matrices, E21, E31, and E32, 1 for each position below the diagonal. The full elimination reads E32 times E31 times E21 times A equals U. To isolate A, we invert both sides. A equals E21 inverse times E31 inverse times E32 inverse times U. that product of inverses, is L. The critical test is whether those inverses produce clean multipliers when multiplied together. Let's check with concrete numbers. Take E21 with multiplier 2, so it has -2 in position 2, 1. Take E32 with multiplier 5, so it has -5 in position 3, 2. And set E31 to the identity for simplicity. The question is, does L end up with the clean multipliers 2 and 5 sitting neatly in their respective positions? Now let's multiply the E matrices, E32 times E21. Rows 1 and 2 come out as expected, but look at row 3. The -5 from E32 multiplies the -2 from E21. In position 3, 1, we get -5 times the -2, which equals +10. So the E product is 1, 0, 0 on top, -2, 1, 0 in the middle, and 10, -5, 1 on the bottom. That 10 is a parasitic cross term. It's an artifact from one elimination matrix corrupting another's multiplier, and this is the problem with multiplying E matrices directly. Now let's multiply the inverses instead in the opposite order. E21 inverse times E32 inverse. E21 inverse has +2 in position 2, 1. E32 inverse has +5 in position 3, 2. The product gives us L, 1, 0, 0 on top, 2, 1, 0 in the middle, and a 0, 5, 1 on the bottom. Position 3, 1 is 0, no cross term at all. The multipliers 2 and 5 sit cleanly in their natural positions. Why does this work? When we multiply inverses in the right order, each inverse only modifies a row that later inverses don't touch. The multipliers slide into L without any interference. Let's return to the 2 by 2 example from before. We had L equals the matrix 1, 0, 4, 1, and U equals the matrix 2, 1, 0, 3. Now we'll extract the pivots from U into a diagonal matrix D. The pivots are the diagonal entries of U, which are 2 and 3, so D equals the matrix 2, 0, 0, 3. Next, we divide each row of U by its corresponding pivot. Row 1 of U is 2, 1. Dividing by the pivot 2 gives 1, 1/2. Row 2 of U is 0, 3. Dividing by the pivot 3 gives 0, 1. We call this new matrix U prime, 1, 1/2, 0, 1. Now we can write A equals L times D times U prime. That is A equals the matrix 1, 0, 4, 1 times the matrix 2, 0, 0, 3 times the matrix 1, 1/2, 0, 1. Notice the beautiful symmetry in this factorization. L has 1s on its diagonal, U prime also has 1s on its diagonal, and D holds the pivots sandwiched in between. For symmetric matrices, it turns out that U prime equals L transpose, which gives us A equals L times D times L transpose, a powerful and important form that we'll explore in another video. L is free and A equals LU has 3 major payoffs. First, efficiency. To solve AX equals B for many different right-hand sides. Without LU, you repeat for elimination each time. With LU, you factor A just once. Then for each new B, you solve Ly equals B by forward substitution, working from top to bottom, and then solve Ux equals Y by back substitution, working from bottom to top. 2 fast triangular solves replace full elimination every time. Second, conceptual clarity. L records what you did every elimination step. U records what you got, the reduced result. Equals LU is a complete diary of elimination. Third, foundation. LU leads to LDU, Cholesky factorization for symmetric positive definite matrices, and PA equals LU when row exchanges are needed to handle 0 pivots. Every elimination you perform from now on, write down the multipliers, place them below the diagonal with 1s on the diagonal. That gives you L. You already have U from elimination. A equals LU will be sitting right there, waiting for you. The factorization was hiding in your work all along. L is the lower triangular matrix with ones on the diagonal and the multipliers stored below. It comes to you for free from elimination. U is the upper triangular matrix, the result of elimination. Put them together and A equals L times U. The factorization is complete.